Okay, I think we can start now. Let me just check once. Okay, so I think we can start now. So, good evening, everyone. I welcome you all to this week 5 live session on the NPTEL course on machine learning and deep learning fundamentals and applications. So, this course is provided by Professor Manas Kamal Bhuyan, who is a professor in the Department of Electrical and Electronics Engineering, IIT Guwahati. So, in this particular week, what we'll be doing is basically we'll first solve the quiz of week 4, and we'll see the implementation of SVM in Python. So that is what we are going to do in this particular session. So to begin with, let's first solve the quiz, and then after solving the quiz, we'll be doing the implementation in Google Colab. Like in the earlier case as well, we have implemented the feature extraction part. We have seen the database, how to handle the database in both PyTorch and in TensorFlow. So likewise, we'll be using some custom data set as well as some standard data set to classify them using SVM. So you have studied that there are several versions of SVMs that are available. One is linear SVM, another one is the polynomial SVM, for example. It could be cubic, it could be quadratic, etc., etc. So we'll be implementing them on Python. Okay, so let us start solving the question. You might find the questions are basically ordered in a haphazard manner. So uh, the questions are like in a jumbled manner. So to begin with, the question states that to avoid the problem of ambiguous region of a linear discriminant function for C categories, we can. So let's say you have C number of categories. So if I just try to illustrate it, so let's say this is category 1, C1, then you have, let's say, category 2, this is category 3. Let's say we have 4 categories, C4. So to do the classification in an in an to avoid the ambiguity, so what we need to do is basically the classification boundary should be like this. So there should be 4 discriminant functions which can separate these classes. So over here you can see that this particular region is basically solely given for class C1. So similarly, this particular whole region in between these two lines, you can see uh, these is basically prescribed for class 4. So similarly over here also this represent the class 3 area, and so as this particular area basically represent class C2. So this is what basically uh, avoiding ambiguity basically means. So over here, let's say you could have chosen some sort of function, some sort of representation like this. Let's say you have a class C1, let's say you have class C2, and you have, let's say, class C3. So over there, if you choose your discriminant function to be just like this, so over here, you can see that there are certain ambiguous regions that are available. For example, over here in this particular region, for example, if I choose the another classification decision boundary to be this, so you can see that C3 information, let's say this particular region is for C1, this particular region information shares the information of C2 as well as C3. So that means it is not able to classify C3 well, and hence it is creating some sort of an ambiguous region of classification. So we need to avoid these kind of decision boundaries such that we can do a better classification. And that particular boundary would be when you choose your boundary to be like this. If you choose your boundary to be like this, and just consider this green line does not exist. So over here you can see that this is the decision surface that I'm plotting. So this particular area is solely given for C1, this particular area is solely given for C2, and this area is given for C3. Now, uh, now we can understand, let's say you have C number of classes. So there will be how many such decision boundaries? There will be C number of such decision boundaries. So this is, let's say, G of C1, let's say this is G of C2, and let's say this is G of C3. So there are three different decision boundaries that you can draw so that you can avoid the ambiguous region. Now, for let's say your class, let's say you have an X, the data that is basically coming from, let's say, some class C, you need to predict that whether X belongs to either C1 or C2 or C3. Let's say you want to predict, let's say you want to predict X belongs to C1. So you have to calculate G C1 of X, G C2 of X, and G C3 of X. You have to evaluate these decision boundaries for each of the classes. Then you have to see, if you see your decision, then if you see G of C1 of X is greater than G of C2 of X and G of C3 of X, so then you can state that your linear function, your linear function G of C1 of X is highest. So therefore, you can state that X belongs to C1. So you have to see, to get into your data to belong to that particular class, the discriminant function for that particular class evaluated on that particular data should yield the highest value. So then only you can say that that particular sample belongs to so and so class. So let us see that what are the options that they have given. So the first option states that define C linear functions GI. 1 second. Yeah. So the first statement is define C number of linear functions GI for each of the classes. So already we have told that if you have four number of classes, let's say if you have four number of classes, to do a unambiguous classification, so you have to have uh, four number of decision boundaries. So as in this particular case also, you have three classes to do unambiguous classification, and to rely upon unambiguous region of classification, you have to have three number of decision boundaries. So therefore, this particular statement is correct because they are saying that define C number of linear functions GI for each of the classes. So that is what we have already told, that if you have C number of classes, there will be C number of such discriminant functions. So this particular option is correct option. Then the second option states that assign X to omega j if gix is less than gjx for all I not equals to j. So this is also true. For example, if you want to see that if your X belongs to C1, then GC1 of X should be yielding the highest value. So that means if, so the condition is if X belongs to omega j, so the Gj of X should be greater than Gi of X. And obviously you have to follow the criteria that I is not equals to 0. Obviously that is true for all the cases. So this is what you can see over here as well. So Gi of X is less than Gj of X. So that means this particular option is also correct. Now let us see what is the third condition. That is, take a linear machine classifier. So linear machine classifier, already you have seen that let's say you have C number of such classes. So for C number of such classes, you have to create a discriminant function. So what you have to do is basically either you can train there will be C number of such equations, and you have to solve those C number of simultaneous equation to get the weights of the particular decision boundary. And therefore, this particular C number of linear equation basically suggests the classifier to be a linear classifier. And so to say, these are called the linear machine classifier. So this particular option is also correct. So therefore, as all of these options are correct, see, your final answer should be all of the above. Okay, fine. So the next question states that which of the following statement is true about the learning rate in gradient descent? So before just going to the going directly to the solution, let us just write the equation of gradient descent, that is Wn plus 1. Let us consider you are at iteration n plus 1th iteration is equals to Wn minus uh, eta, that is learning rate, and then del E by del W. So E is basically the error function. It could be L2 error, it could be L1 error, it could be binary entropy, binary cross entropy, categorical cross entropy, based on whether your task is classification, you'll be using entropy based loss functions. If your classification, if your task is basically regression based task, so then you'll be using any of the L1, L2, or there are several sort of norms that you can use. Fine. So let us now consider the error versus weight curve. And let us consider the error surface is a convex surface. Okay. Now, let's say you start at a position this. Let's say your eta value, eta is very, very high. Or let's say, we can start with eta value is very low, and then it will be easier to understand. So when your eta value is very low, so you can formulate that, let's say eta value is eta is equals to 0.00001. So Wn plus 1 is equals to Wn minus eta, which is very small value, and then you multiply with the gradient of error with respect to the weight file. Now you can see, let's say your gradient value, so let's say this gradient value is, let's say, 100. So even if you multiply 100 with this particular number, you'll see that the decimal place will shift over here. So that means if you're, if I just do it like this, it would be more clear to understand. So 0.00001 multiplied with 100. And let's say, as because you are residing at this particular point, you can see that the gradient is basically moving in this particular direction, right? So gradient is moving in this particular direction, and the gradient, let's say this gradient is basically negative. So let's say this particular value is minus 100. So it would be minus multiplied at this particular area. So minus minus plus, it would be, let's say, 0.001. So you can understand that you're adding W with a very small value. So in the, if let's say this was nth iteration, in the n plus 1th iteration, it would reach, let's say, over here, just this much of increment, n plus 1th iteration. So that means if your eta value is very low, the increment of the weight parameter or change in the value of W will be very slow, and which basically indicates the convergence, because what you are trying to do is basically trying to reach the minima. If you reach the minima, then the derivative will uh, reach zero, and therefore you can understand this particular whole thing will go to zero, and Wn plus 1 is equals to Wn strictly. So that means at that point your iteration, at that point your optimization process will be stopped, because your current weight value is equals to previous weight value. Now, so this particular thing basically refers that convergence of the gradient optimization process, gradient optimization process is low, is slow actually, sorry. Now let us consider your eta value is very high. Eta value is very high. So if your eta value is very high, let's say eta is equals to 10 to the power, let's say 4, or let's say 10 to the power, let's say 100. So now you can see that your Wn plus 1, this equation will now be Wn plus 1 is equals to Wn minus 100 multiplied with minus 100. We considered that del E by del W is equals to minus 100. Let's say. So what would happen? So in this case, Wn plus 1 is equals to Wn plus 10 to the power 4. So now you can see in the previous case, when eta value was low, we were adding a very small value with Wn. But in this particular case, when eta value is very high, we are adding a very high value with the Wn. So that means you are staying over here in the nth iteration. So this red color basically means when eta is low. But when you use the eta value to be very high, when your learning rate is very high, then uh, you're adding a very high value with Wn. So initially your position was at Wn. So this one, now with addition of very high value, let us consider you have reached this point. So this is your Wn plus 1 when eta very high. So in this particular region, what you can see over here, if you calculate gradient at this particular point, you can see that the gradient is positive. So now if I do the second, if I move to the second iteration, let's say Wn plus 2 is equals to Wn plus 1 minus eta value is still that is 100. And let's say in this particular region, when you calculate the gradient, let's say del E by del W, let's say this del E by del W is 10. So you multiply this with 10. So what will happen? You see Wn plus 1 is minus 10 to the power 3. So now you can see what was your trajectory. Just track down the trajectory when your uh, eta is very high. Initially you started at this point, then you reached here. Now again, your W in this particular equation, you can see that Wn plus 1 minus 10 to the power 3. That means again the value will be decreased. Let's say now you are reaching at this particular point, which is Wn plus 2. So in this way, you can see that initially when you started with eta value very low, your process of convergence was very slow, because your step, in each step, you are adding a very small value. This is a very small value, very small value. But when you choose your eta to be very high, now you can see that your path will be like this. So you can see there are multiple sort of oscillations. So it is going like this, like this. So you are getting several sort of oscillations to reach the maximum, to reach the extrema point. So the conclusion from this particular region, so the conclusion that you can draw over here is yeah. So the conclusion that you can draw from here when eta is very high, there will be large number of oscillations. So now let us see what are the options that they have given, and we'll discuss, we'll try to discuss all of them. So a very high learning rate may lead to oscillations. So that we have seen that a very large value of eta will basically give you very large amount of oscillations like this. So this one is correct. A lower learning rate may lead to faster conversions. So over here, you can see that if you choose your learning rate to be very low, you're adding very small value in each iterations. So that means your progress is very slow from here, then from here, then from here. So this progress is very slow. So you'll take large amount of time to reach this particular point. So this is the point that you want to reach. And to reach this particular point, you have to go for multiple iterations. So the process of convergence, so the convergence is slow. So that means, and already we have discussed over here as well. So a lower learning rate may lead to faster convergence. That is false. So rather it would be the correct statement should be the convergence is slow. So this is incorrect. The learning rate does not determine the step size, the size of the steps taken towards the minimum. So they are telling that learning rate does not determine the size of steps, but it is basically uh, taken consider it basically takes into consideration that if you choose your eta to be very small, so your step size is very small. So that means you'll take large number of time to reach the minimum. Whereas if you take eta value to be very high, you can see that you get several oscillations to reach this particular point. So that means indeed eta plays an important role to determine the step size to reach the minima, because your main aim is basically to reach this particular minima point, this particular minima point. Because when you reach this particular minima point, del E by del W will be equal to 0. So eta multiplied with 0 will be equal to 0. So that means Wn plus 1 is equals to Wn. That means your optimization will process will be stopped there. So that means this particular option is also incorrect option. The learning rate has no effect on convergence of gradient. So again, this is incorrect because you already have seen that if you choose learning rate to be very small, then your convergence will be low. If you choose learning rate to be very high, then you will get several sort of oscillations. So that means eta again indeed has a great effect on convergence of the gradient descent process. So therefore, this particular option which says that there is no effect, so this is incorrect. So therefore, option A is the correct option for this particular question. Okay. So the next question states that, uh, 1 second. The next question states that In the perceptron algorithm for a binary classifier, what happens to the weight when a positive misclassified point is encountered? So, uh, as you can see, the binary classification problem. Let me just draw a binary classification problem in front of you. So let's say this is the feature plane. Let's say you have two features, x1 and x2, and based on x1 and x2, you have plotted the classes like this. So let's say this is your positive class, and let's say these are your negative class. So if you choose your decision boundary to be like this, if you choose your decision boundary to look like this, so let's say this is omega minus and this is omega plus. So let's say you have this function as, let's say, g of x. So x belongs to omega 1 when g of x1 is greater than g of x2. Similarly, x belongs to omega 2 when g of x2 greater than g of x1. So this is the fundamental criteria that we have seen earlier as well. If let's say your discriminant function is g of x, you'll be calculating so you'll be calculating the uh, value of g for for both the cases, and then you'll see that if it basically, so precisely, let me just, as because they are positive class and negative class, instead of omega 1 and omega 2, I can write them like this as well. So we can consider that if g of x is greater than 0, then x belongs to class positive. If g of x is less than 0, then we can consider x belongs to class negative. So this could be a precise definition that you have a negative class. So for negative class, if you evaluate this g of x, you will get less than 0 value. And if you have uh, x belonging to positive class, then your g of x will be greater than 0. So that is the that is the decision rule. So this is decision rule. But you can see that the decision rule is not a unified rule. So there are two rules for two different classes. So now if I just can consider that this omega 1 class, basically, let's say it will give you so over here the decision rule is not unified. So that is the first point that you have to consider. The decision rule is not unified. So to make it a uniform decision rule, to make a uniform decision rule, sorry, you can write it like this. Let's say if x in the training set, in the training set, in the training set, you know that whether x belongs to omega 1 or omega 2 or omega plus or omega minus, because based on that, you will be training your classifier. So x belongs to, let's say, omega plus, then your rule is g of x should be greater than 0. Then you can say that that signifies that signifies proper classification or correct classification. Now in the second case, if x belongs to omega minus, so what you will do, if you see your x belongs to omega minus, you will negate the value of x. So that means instead of x, you will be then passing g of minus x. And then what you are expecting is it should give you a greater than 0 condition. So if it is greater than 0, then again it signifies that you have done correct classification. So let's say your g of x is let's say your g of x is basically A transpose x. So for positive class, it will give you 0. So x belongs to, so initially we were writing g of x. Now let us try to define the function. Let us try to define the equation of this particular line. So the line equation of this line is A transpose x. So we can consider this is basically y equal to mx, as because this particular line is passing through this origin. So I'm writing it in terms of A transpose x. So that is the standard form of writing these sort of uh, equations in the machine learning literature. So when x is positive. Now what you will do when x belongs to omega minus, generally, when x belongs to omega minus, it should give you g of x less than 0. Now, to remove this particular criteria, what we are basically saying that instead of x, now you will be passing minus of x. So that initially it was giving less than 0. When you pass minus x, it should again give you greater than 0. So that means your decision rule for both the class are now uniform. And how it will look pictorially, that means you started your problem like this. Now you can say that the training data in the training data set for omega plus, you will keep the data as it is. X will be positive as it is. Whatever value of x is there, that you can write it as it is. But now you are negating the value of the omega minus class. So if you negate the value, the what will be the position? So x values are negated. So that means this will come in this side, and y values will also be negated. So that means they will come in the third quadrant. And your decision surface is same as, so it should pass through 0. So please pardon the drawing. So over here, you can see that the decision boundary will still be g of x, which is A transpose x. So now you can see for this particular region also, when you evaluate g of x, it would be greater than 0. And for the negative class, what you will do, you will put g of minus x. This will be g of minus x. They will also give you greater than 0. Whereas in this particular case, over here, g of x was greater than 0. In this particular region for the negative class, it was g of x less than 0. Now, as you have negated this data, over here. So if I just rub this and rewrite it again. So as you have negated the data, what is happening is basically you are getting the, for correct classification, your decision rule is now g of minus x is greater than 0. I hope this part is fine. So for this particular area, the rule is g of x is greater than 0. For this particular area, the rule is g of minus x is greater than 0, as because your data is belonging to the negative class. So till this point, let me just again summarize. You started with your problem with two different decision rules. Now you have converged those two different decision rules in a unified decision rule. Now, when you'll have misclassification, so you have to, while training the model, you must make some sort of misclassification. Then only you will get the error, and the error will be optimized through gradient descent based optimization technique, weight optimization technique. And over here, A is basically those weights, or to be more precise, these are the learnable weights. Now, if you do misclassification for misclassification, so for misclassification, when you have misclassification, let's say for this particular class, when let's say x belonging to positive class, and you are evaluating your g of x, which is A transpose x, and let's say if it is giving some negative value, or let's say g of x is A transpose x is less than 0. In this particular condition, you can see that for correct classification, your decision rule was always greater than 0. Now, let's say for misclassification, when x belongs to omega plus class, omega positive class, that means in this particular area, you are evaluating with some value of x, and you are getting your value, your g of x evaluated value is negative 1. So that means this indicates misclassification. So that means you are doing you are incurring some sort of loss. So now we have to write the corresponding loss function. So in this particular case, loss basically means we write it like this: A transpose x minus of A transpose x for all x misclassified. So what is the meaning? So the meaning is basically whatever x you put, if you are getting the value less than 0, so that means you are doing some sort of loss. So we will be acquiring all those misclassified samples, and we'll evaluate this A transpose minus of A transpose X, and then we'll add all those cases. So this will acquire all the misclassified samples. So this is the loss function. And then what we have to do to update the weights, we have to go for gradient descent based optimization technique. So now let me write the gradient descent based optimization technique. So till this point, your loss function L of A is basically summation A transpose X for all X misclassified. Your training decision rule is basically G of X, which is again A transpose X, should be greater than 0, irrespective of X belongs to omega 1, X belongs to omega 2. A transpose minus X greater than 0. So this is your decision rule and this is the loss function. So what the question states that you have a binary classifier problem, binary classification problem. So as what we are doing, let's say this is your positive class and let's say this is your negative class. You have done the negation. So this is the function that is g of x, which is A transpose X. Now let's say you are doing misclassification. So for misclassification, what you are getting g of x, which is A transpose X, and let's say your x belongs to omega plus class. So A transpose X is less than 0. So that means you are doing some sort of misclassification over here. So if you're doing some sort of misclassification, you have to uh, update your weights. So that means your weight updation equation would be same as what we have seen in case of gradient descent. So this would be eta multiplied with gradient of L of A. So that means you have to take basically the what you call we have to take the gradient of L with respect to A. Now for misclassification, so for misclassification, your L of A is basically minus A transpose X. And let's say your X in this particular, as per this particular question, when it belongs to positive misclassified point. So that means when let's say X, if I just write when X belongs to omega 1. So when X belongs to omega 1, you can see that your A transpose X itself is negative. So that means your A transpose, and you have a minus sign over here. So you have a minus VE, and your A transpose X already have seen for positive class, for misclassification, the value is again negative. So the summation output will be positive. So that means I can equate it with like this. It would be A transpose X minus, it would be minus 1 multiplied with the value is negative. So let's say the value is something like minus A transpose X. So it is minus A transpose X. Or let's say the summation minus 80x. So I can take the gradient over here. So it would be del L by del A. So if you do del L by del A, it would be how much? It would be with respect to A, obviously. So if you take with respect to X, it would be minus summation of X. So if it is minus summation of X, you can write that A n plus 1 is equals to A n minus eta and del L by del A. So the del L by del A value is A n minus eta, and then you have uh, minus X. So it would be A n plus eta into this thing. So A n plus 1. So over here, you can see that A n plus 1 is equals to A n plus eta into summation of X. So that means initially your value was A n. Now you are adding the value of A n with some positive quantity. So that means the answer should be it is increased. I have seen that in the week's quiz they have written it remains same, but this is not the correct answer. The correct answer is it is increased. Okay. So the next question states that let Wij represents weight between node I at layer K and node J at layer K minus 1 with a given at a given multi-layer perceptron. So I don't think so anyway you have studied what is multi-layer perceptron, but still you can just think that you have some sort of a weight, whether it is multi-layer perceptron, SPM, whatever it is, you can think that you have got some sort of a neural network architecture and you have got some sort of weights, that is WIC. And what it is saying is basically the weight updation using gradient descent method is given by, so alpha and E represent the learning rate and error in the output respectively. So we already know that Wij of, let's say they are annotating with Tth iteration. So T plus 1 is equals to Wt Wij. They have given the subscript Wij. So that is Wt minus their learning rate is now alpha. So alpha, and you have to take gradient of error with respect to the weight value. So therefore, it would be Te, I mean del E divided by del omega Ij. So this is the form of the gradient descent equation. And at the same time, you will see this is a common practice that you take the range of alpha in between 0 and. So this is a common practice. If you take alpha to be greater than 1, you can think that uh, you might incur some sort of an overshooting condition to the minima because you're taking alpha value is quite high. Then what would happen is basically you'll get multiple number of oscillations over there in the error space. So this particular option is incorrect because they are putting a plus sign over here. So this is incorrect. Then you can see that Wt plus 1 is basically they are only writing the gradient part. So the gradient part only just by putting the gradient part, that is also incorrect because you need to incorporate the previous value as well. So in the last option as well, you can see that they are also again they are not incorporating the previous value. So this is also incomplete equation. So the complete and correct equation is basically Wij t plus 1 is equals to Wij t minus alpha into gradient of error with respect to the Wij, that is the weight, and the range of alpha is basically in between 0 and 1. Fine. So the next question states that a 4-input neuron has weights 3, 4, 5, 6. The transfer function is linear with a constant proportionality being equal to 3. And the inputs are 6, 12, 10, and 20. So if I just try to formulate the equation or formulate the structure of a neuron. So the structure of neuron is basically, let's say you have a neuron like this. And let's say you have x1, x2, x3, and x4. You have 4 inputs, and the value of the inputs they have given already. I'm not writing the value of inputs right now. So they are connected with this neuron with some connecting weights. So that is weight 1, that is weight 2, weight 3, and let's say weight 4. And you do summation wi xi. So this is the first process that happens inside the neuron. So this is called linear combination. And then what you have is basically you have a transfer function. Let's say this part corresponds to a transfer function, which is in general is basically some sort of an activation function. So I'm not going to use this particular term now because late in subsequent weeks you'll see that what this particular activation function means. But for the time being, let us now consider there is a another functionality that basically works over here. That is, let's say, a transfer function. It could be a very simple transfer function as a thresholding function. Let's say this is +1 and this is -1. It could be a threshold based function. Over here for this particular case, let's say this is SGN of X. If your X axis to be annotated as X. So it could be any other thing, like for example, in this particular question, they have written that the uh, transfer function is linear. So that means it should be a equation of line, obviously, with a constant proportionality. Let's say y by x is basically refers to the output divided by input, is basically refers to the transfer function in a very loose sense, because there are some other uh, conditions are also associated with this, because let's say the uh, initial conditions has to be 0. So I'm not going into the control system lecture. Let us now just mathematically say y by x or output by input basically gives you the transfer function. Now the transfer function is linear and the proportionality constant is basically 3. So that means this particular thing is 3. The proportionality constant is 3. So your y is equals to 3 into x. So that means you can consider that it is a equation of line y equal to mx, and therefore this particular transfer function is a linear transfer function. So in this particular question, they have stated that this is linear transfer function with a slope 3. So now let us write the equation for this particular case. So when you have 4 sort of inputs and the connection edges have the corresponding weights like W1, W2, W3, and W4. The first operation is a linear combination operation. So I can write the linear combination to be, let's say, x hat to be summation Wi xi. So it would be W1 x1, W2 x2, W3 x3, and W4 x4. So in this particular case, the values will be 6 multiplied 3, 4 multiplied 12, then 5 multiplied 10, and 20 multiplied 6. So therefore, it is 18, then uh, 48, 50, and 120. So let me just add them up. So this is 236. Fine. So this is x hat. So your x hat is 236. And from this particular, so we have reached this particular part. We have reached over here. So we have got x hat. And the output is, let's say, y. And in the question, they have told that y by x hat is equals to 3, as because the function is a linear function and the proportionality constant is 3. So your output is equals to 3 into x hat. So our x hat is 236, which basically is 708. So in this way, you can evaluate the value of y. Okay, so we have another some sort of a controversial question over here. Let me just skip this one. I will come back to this particular question later. Okay. So the next question states that you have been given a sort of a training data set, which comprises two features, x1 and x2. You have the classes as well, that is positive class or negative class. So I have taken the image from the quiz website. The image was quite bloody. So over here also this particular image is bloody only. So you can refer to the original image from the quiz website. So, and corresponding to that, we have got the Lagrangian multiplier values as well. So we know that for training an SVM, we have to find out that what are the support vectors. And we know for the support vectors, the Lagrangian multiplier should be a non-zero Lagrangian multiplier. If you have a non-zero Lagrangian multiplier, you can state that those points are basically the support vectors. So in our case, we have got a support vector here because you can see that your Lagrangian multiplier lambda I is basically a non-zero value over here, which and it belongs to a positive class. Similarly, we can see that the second data point, which basically belongs to the negative class, is also yielding the uh, positive or non-negative on actually non-zero lambda I value. So that means these two refers to the support vectors from each of the classes. So in our case, we have positive class and negative class. And we also know that as because this SVM basically tries to generate a sort of a equation of line, because we have seen that let's say if your data set looks like this, your data set looks like this. In this region for both the classes, in this region, you can see you can plot infinite number of lines, but you need to find the line in SVM which corresponds the maximum margin. So in case of SVM, the main target or the main objective is basically to find out the corresponding line which yields maximum margin from the support vectors of both the classes, obviously. So let's say this is the optimum line that SVM predicts, and let's say this one is a support vector, and let's say this one is another support vector from both the classes. And what we have to do, we have to calculate the distance. So let's say this is D1, and you have to calculate this distance. This is D2, and we have to maximize the margin. That means D is equals to D1 plus D2 should be maximized. And to maximize this, we have already seen that we solve a series of equation. We have to first we encounter a constraint optimization. To make the constraint optimization an unconstrained one, we have to form a Lagrangian. And we had solved the equations of the Lagrangian and we got the solution of the equation as well. And we saw that the Lagrangian multiplier is a non-zero Lagrangian multiplier for the support vector cases, and the support vectors are quite important so as the SVM is concerned. Okay. And we have also seen, I'm just directly referring to the equations, and these equations you can find it in the week's lecture as well. So over there, the weights have to be optimized such that you can get the maximum margin. And when you solve all the Lagrangian equation, all the optimization equation, you'll see that the equation of weight basically corresponds to lambda I, yi, x I. So in our case, we can see that uh, we have two different. So let's say this is Wi, and even I can write. I can write it in the next stage. So For each of the W, the equation is this. Lambda I, yi and xi, these will be multiplied and then the summation will basically occur. So uh, for the for for the equation of line that basically the SVM will predict, the generic equation is simply, I can write it as W1 x1 plus W2 x2 plus bias or the intercept of the equation is equals to 0. So this is a generic equation of a line. Generic equation of line that SVM predicts. So now we have to find the value of W. We have to find the value of W1, W2, and B. So to get the value of W1, we have already seen this particular equation. So we'll be using this equation. So this is lambda I yi. Now you can see initially I was talking about x. So x was a single dimensional value. Now instead of having a single dimension value, now we can see that we have two different dimensions. That is x1 and x2. So I can further generalize the equation as x1. So I can write it as let me write it like this for all I. So it would be lambda 1, y1, x11, lambda 2, y2, x1. So what is lambda 1? Lambda 1 over here is basically 65.52. Then you have y1, which is plus 1. And then you have x11. So this is what x11 means. That is 0.38. So this is 0.38. Then you have lambda 2. So lambda 2 is again 65.52 multiplied with what is y2 over here? Y2 over here is minus 1. So therefore it is minus 1. And then what you have is basically x12. So this is x1. So this is x11. This is x12. So therefore I can write it as 0.49. So if you add all these things up, so you will get the value. I have already noted down the value. So the value is minus 7.20. So this is W. Then again, you have to find the value of W2. So again, the equation is x1i, yi, lambda I for all I. So therefore, I can write lambda 1, y1. Sorry, it would be x2. So it would be x21 plus lambda 2, y2, x22. So your lambda 1 is 65.52, y1 is 1, and x21, now over here x21 is this one. So this column is basically x2. This is the first element of x2. So this is 0.47. So you can write 0.47 plus 65.52 multiplied with minus 1 multiplied with x22. So that is 0.61. Sorry. So W2, if you calculate all these values, you will get W2 to be minus 9.17. So this is W1, this is W2. Now we have got the values of W1 and W2. Now we just by looking at this particular value of W1 and W2 itself, we can say that this is the correct answer. But we also have to basically evaluate the value of B or the intercept. So now how to uh, uh, find the value of the intercept. So to find the value of intercept, what we can do is basically, as because we can see that this is the equation of the generic function, generic lines function. So what I can do, I can write the equation in this particular fashion. For example, W1 into X11 plus W2 X12 uh sorry X21 plus B1 is equals to 0. This is for the first case, and then I can write again W1 X 12 plus W2 X 22 plus B2 is equals to 0. So what I am just inferring is it is basically using these two coefficients I am constructing a first line, and using these two coefficients I am constructing second line. And I don't know what is the value of B1 and B2, but I do know what is the value of W1, W2, X1 and X11 and X21. So if you try to find the value of B1, so it would be minus W1 multiplied with this one. So W1's value is minus 7.2 multiplied with 0.38. And then what we have over here is basically W2. So the value of W2 is how much? The value of W2 is 9.2, sorry, 9.17. 9.173 multiplied with uh, X21. So X21 is 0.47. That is 0.47. So after you do all these things, you will get uh, the equation as, oh, okay. So from this particular representation, what you can see is basically this belongs to class omega 1 or the class plus 1, and this belongs to class minus 2. So that means for these two classes, the class specific equation would be W X plus B. I'm writing the generic function, that is W transpose X plus B should be equal to 1 for Y belonging to plus class, and W transpose X plus B will be equal to, so this is for the plus class, and you can just revert the formulation for the negative class. So this is quite logical. So we already have seen in each of the discriminant function classes as well that if your data belongs to plus class, the final equation should also equate to plus 1. Otherwise, it should equate to minus 1. So from this particular logic, so I, instead of going to the equation of line, you can refer to the equation of class. So if you solve B1 like this, so over here you have plus 1. If you solve B1 like this, then what you will get is basically I have written down the values. So just let me check the values once. So the value would be 8.05 over here, and the value of B2, similarly, the value of B2, you just put the values and you will get 10.12. Okay. So you can see that B1 and B2 are you have evaluated. Now you have got uh, two values of the intercept. So as because we need a unified formula for the equation of the optimal line, what we have to do is basically we have to take average of these two intercept values. So this would be B1 plus B2 divided by 2. So if you take average, it would be 9.085. So you can write it as 9.09 over here. So therefore, the optimal equation of line is basically minus 7.2 x1 minus 9.17 x2 plus 9.09 is equals to 0. Okay, so uh, in refer to question number 8, a new test sample you have found the class of the given sample is. So you had several data points over here. You have constructed SVM. You have got the optimal equation, optimal line of equation is this minus 7.2 minus 9.17 blah blah. So based on this particular equation that you have got as the decision boundary, you have now got a test sample. Now you have to put the test sample values on this particular line of equation, and you have to see that whether the 0.05 comma 0.05, this particular test sample belongs to either class +1 or -1. So to do that, what we have to do, we have to again refer to question 8's answer. So the Q8 answer was minus, let me just write the equation, minus 7.21 x1, then you have minus 9.173 x2 plus 9.09 equals to 0. So this is what is basically your g of x is. Now, uh, for sake of simplicity, I can write g of x1 and g of x2 is. Now you have got a test sample. So you put 0.5 comma 0.5 in this particular equation. So it would be minus 7.21 multiplied with 0.05. Sorry, it would be 0.5 only. So it would be 0.5 minus 9.173 multiplied with 0.5 plus 9.09. So if you solve this particular thing, your answer is 0.8985. So you can see this is basically a positive number. So as because your G of test sample, so half comma half is greater than 0. So that means it is basically yielding a positive value. That means the class identity. So the class identity would be class. So that means it would be in the positive class. Okay, fine. And the last question states that what is the main objective? What is the main objective of a support vector machine? So we know that, let's say your data set looks like this again. So this is just a recapitulation of the SVM part. So let's say your data set looks like this, and you have put uh, you can put lines, uh, infinite number of lines in this particular region. So if I just draw the region, these are the class specific cluster regions. So uh, to put a decision boundary in between these two classes, you can understand that you can put n number of such lines. So it could be like this, it could be like this. So you have infinite number of lines. You can put infinite number of lines as a line of solution. or the decision boundary, so to say. Now you have to find the which one is the optimal among the all such decision boundaries. So this is the solution region. So in this particular solution region, you can have n number of lines. You need to find that which of the line is the optimal one, which gives you the highest confidence of classification. So for that, SVM came into picture, and SVM stated that you first try to locate what are the support vectors from both the classes. So let's say this is the support vector and this is also a support vector. Let's say maybe the picture is not that precise. So, so this is these are the support vectors, and as these are the support vectors, you can understand that you'll be calculating the perpendicular distance from this particular vector to this particular line, and similarly from this particular vector to this particular line. So therefore, you have to calculate D1 and let's say D2. So margin of classification is basically D1 plus D2, and this should be maximized such that yi given W transpose X plus B should be greater than 0. So these things already you have seen in the SVM's lecture. So the main purpose of SVM is basically to maximize the margin corresponding to a particular decision boundary. So you have infinite number of decision boundaries that you can put in between this particular solution region, but you have to choose that particular line which gives you maximum margin for classification. So that means your main target is to select that hyperplane to separate the classes, which gives you maximum margin. That's it. So to maximize, so let us see the like, let us see the options that they have given. So the first option states that to maximize the number of support vectors. So the main objective of SVM is not to find maximum number of support vectors. Rather, it basically tries to maximize the margin of classification, because classification margin that basically plays the main role rather than finding the number of support vectors. So, so this one is incorrect. Then to minimize the margin between class. So this is again, this is not possible, because if you are minimizing the margin, that means you'll not be able to ensure that you'll be doing classification correctly. So therefore, this particular option is also incorrect. So the next option is to maximize the training accuracy. So in, obviously for each and every classifier, the main target is to maximize the accuracy. But in respect to this, if you see the option 4, which basically states to find the hyperplane that separates the classes with maximum margin. So this is the cause. And if you are able to find that particular line which gives you maximum margin, so obviously you will get this condition, that is maximize the training accuracy. So that means this is the cause and this is the effect. So that means effect cannot be the correct answer. Rather, this particular answer, that to find the hyperplane, that means you're trying to find the decision boundary that separates the classes with maximum margin. So that is the main motto of SPM. Again, the point is in the NPTEL quiz forum, I have seen that they have marked a wrong option to be the correct one. But again, the answer that is given by NPTEL is incorrect. Okay. So the next question states that which of these is true about discriminant classifiers. So we have already seen several sort of discriminant classifiers in the after we have seen the night Bayes classifier or the Bayesian classifier in general. So when we started discriminant functions in general, so we wrote that g of x is to be p of omega given x, right? So this is P of omega given x is basically the a posteriori probability that we have seen in Bayesian decision rule. And I can write it as again as P of omega, that is basically the prior probability or the prior density of of a particular class. And then I can multiply it with x of x given omega. So this is basically nothing but the class conditional density. So you have prior density as well as class density. You multiply these two, and there is a denominator term as well. But the denominator term is just a scaling factor. So that is why we have removed that particular part, because that does not play any role in classification. Now, after that, we had considered that P of x given omega, it is basically coming from a distribution. And we chose that this particular distribution to be a Gaussian distribution. So we chose that this particular data is basically coming from a Gaussian distribution. And then we also talked that instead of taking a single dimensional feature, let's say our feature is multi-dimensional or d-dimensional. So let's say it is x1, x2, .. xt. Now, whenever you write d-dimensional features, that incorporates the the univariate Gaussian basically converts to a multivariate Gaussian. So therefore, we wrote the equation of the Gaussian function to be p of xi given omega to be as 1 upon root over 2 pi. Then we had wrote, sorry, so this is to the power half. And then we wrote exponential minus half x minus mu transpose sigma inverse and x minus mu. So that is what is basically the multivariate Gaussian distribution looks like. So this is the equation for the multivariate Gaussian distribution. So over here, this particular thing, initially, if the distribution was an univariate distribution, we had sigma. But instead of having sigma, now we have capital sigma, which is basically covariance matrix. This is called covariance matrix. And we saw in the discriminant functions class, like I think we are in week 5. So this particular class was in week 3, probably. Yes, week 3. So in week 3, we had seen that sigma would have different sort of representations, like sigma 1 square, sigma 2 square, sigma 3 square, sigma 4 square, let's say sigma n d square. So as we have d number of feature values, and all other entries, all other off diagonal entries are 0. So which basically means that their features are statistically independent. Statistically independent. So this was one case of sigma. Another case of sigma was, so there sigma I equal to sigma j for all ins. So that means sigma 1, sigma 2, sigma 3, all are same. So that was one case. And notably, the off-diagonal elements were basically non-zero elements. So, so that was the first condition. So the next condition was the sigmas are inherently arbitrary in nature. Arbitrary in nature. So at that time also, so we had three different conditions. One is basically while classifying them, let's say these were the clusters having mu1 and mu2 being the mean of the point clouds. So the decision surface was basically line, it was basically the perpendicular to the line joining to the mean of the data clusters, and this was an orthogonal bisector actually. So the angle between these two are 90 degrees. So you must have seen some sort of equation like this, mu1 minus mu2. Then you have some sort of W transpose into 0. So these sort of equations you have seen in week 3. I may not be correct in terms of exact expression, but this was some sort of a representation, because this is the equation of the decision surface, and the decision surface as a perpendicular the decision surface as a unit vector in the perpendicular direction to it. Fine. So the main motto is basically, you can see, while we talk about the discriminant function, we have different conditions. We had three different conditions. One is when all the covariance matrices are same, and when first condition is covariance matrices, all the variances are same, and the off diagonal elements are zero. Second one was the variances are different, off diagonal elements are still zero. Third case is all the covariance matrices are arbitrary in nature, but they are sort of same. So for all the cases, the more generalized case is basically this one. This is a arbitrary case. So that means it is not necessary that this particular conditional probability or the conditional density, it should be independent in nature. And that is what we see in many of the cases. In the last class also, probably in week 2, when I showed the first Python implementation, there I also showed that you have different classes, you have extracted features. And in majority of the cases, you've seen that the features from both the classes have some sort of similar attributes. And therefore, they basically jumble up each other, and they are not very good sort of features, so to say, as because they do not have linear separability. So that means in majority of the cases, you'll see the features that you extract have some sort of correlation with each other, and they may not be independent in nature. So that is why assuming the conditional density to be independent, that is incorrect. Okay. Let us now move to third condition. Can perform classification if some missing data points are present. So think about a situation. Let's say you have trained your model. Let's say there is a model, linear discriminant function. So let's say LDF, and you have three classes. Let's say in the last class in the Python demo we had three classes. One is normal ECG, one is supraventricular, that is a type of arrhythmia, and one is ventricular arrhythmia. So supraventricular arrhythmia and ventricular arrhythmia. And we trained our model with some sort of an ECG signal. So this is your P wave, Q, R, S, T. So this is your typical ECG waveforms, and you have trained a LDF. In week 2, we have done this in Python. And now the question states that the discriminant classifiers can perform classification if some missing data point is present. Now let's say, you have a situation like this. Let's say the patient who is basically wearing the wearable device for which basically acquires the ECG. If you have seen in hospitals, they put some leads, chest leads, and then from the chest lead we acquired the ECG. Now let's say by some means the chest leads were loose. The adhesive was not working well. So some of the let's say one of the uh, ECG lead is now detached from the bottle. So as because the circuit is now incomplete, the ECG will not be coming. So what might happen is basically for this particular period, let's say you are getting some sort of signal, and after that what happened is the lead is now detached from the body. So as because it is detached from the body, it will not be able to acquire any signal. So you'll get 0 0 0 0 0, a string of 0. Now, if you feed this particular thing to LDA, will it be classifying properly? The point is obviously it will not be able to classify properly because you are not giving the correct sort of data to the model. So obviously it will not give you correct sort of prediction. So therefore, stating that it can perform classification even if some missing data points are present. So this is not the uh, correct interpretation. So this is not the correct interpretation. At the same time, the second option, they are saying that it is robust to outliers. So outliers we have seen in the last KNN class, that let's say you have two different classes, cat and dog. So if I just take another page, so let me just discuss about two different cases. Let's say you have cat class, you have dog class, and you have extracted two features from both the cases. One is height and another is weight. So in general, dogs have are high in weight as well as in height than the cats. Let's say this is a dog class data. So let's say this is height and this is uh, weight. So you can see this dog class are residing over here. So over here, you can see the height is much higher as well as the width. And let's say the cat class, as because these cats are basically uh, their weight and height is quite small than the dog class. Let's say they are being clustered over in this particular region. In this particular region. So therefore, there is a significant difference between these two classes. So you can see that inter-class separability is quite high, which is very good for classifying cat and dog. Now, let's say I just give you an example. Uh, so this is a type of uh, dog breed. So this is called Chihuahua dog. So the Chihuahua dog, you can see that the Chihuahua dog is quite small in dimension. So therefore, you can see that this is same as the size of a cat. So if you calculate or if you basically take the data from Chihuahua class, even though it is a dog, its value of height and weight might come over here. So this particular point is actually dog, but uh, its data representation seems to have similar characteristics as the cat class. So from the image of the Chihuahua dog also you can understand that even though it is belonging to a dog class, its height and weight is almost same as a cat. So therefore, if you plot the Chihuahua dog's data in this two-dimensional featured plane, which is basically with respect to height and weight, you will see as because its height and weight is not that high, it will lie in vicinity to the point clusters of the cat class. Now, uh, this is a point of this point is called outlier point because it is actually belonging to this particular class, but its features are quite similar to other class, which might uh, mm, which might incur the possibility of misclassification. So for this particular case, let's say you have trained an linear discriminant function. So to uh, do a classification using a linear discriminant function, let's say you had plotted this particular line to be the discriminant function that is g of x. So now you can see that after you train your discriminant function model using this blue data and green data, you have got a equation of line g of x which separates these two classes pretty well, almost exactly 100% accuracy. But if you receive which is actually dog, but comprises the feature same as the cat class, which is an outlier case. So you can see that this particular line, it will classify this magenta point or this pink point. The prediction will be, so the prediction will be cat. So that means you are doing misclassification. So which means that if you encounter a outlier, your classification accuracy may significantly drop. So that means you are not doing good classification when you hit any outlier point. So that means this linear discriminant function, it is not robust to outlier. So by that logic, this is also not the correct answer. And we had seen from the previous uh, slide that the other options are also incorrect. So therefore, in this particular question, none of them are actually the correct answer. But again, this is an anomaly. So they have answered that robust to outliers. So just to ensure our discriminant classifiers robust to outliers. So this is a research paper that I am referring to. If you just search the question as it is, like our discriminant function robust to outliers, you will see this particular paper will come. So this is a paper published in Science Direct. So the highlighted part, it says that while linear discriminant function is widely used for classification method, it is highly affected by outliers, which is commonly occurred in various real data sets. Therefore, several robust LDA methods have been proposed. So that means this discriminant function in general, they are highly affected by outliers. So that means in general, they are not robust to outliers. And so as this particular example also states that when you encounter an outlier, you might do some misclassification. So that is the main point that I'm trying to infer, that if you hit outlier points, you cannot guarantee that your classification accuracy will be robust enough to make a good classification. Using a simple discriminant classifier or LDA based classifier, linear discriminant analysis based classifier. So by that logic, robust to outliers cannot be the correct answer. And you'll see that can perform classification on some missing data points. This is also incorrect. You'll find that in several research papers, to tackle this particular problem, as because the linear discriminant classifiers are not able to do classification well in missing data points, there is a method by which you can tackle this problem that is called imputation of data. So this is the remedy. If you encounter a missing data point problem, then the remedy is imputation of data. Imputation of data means instead of the missing points, let's say your missing points are all string of zeros, you have to put certain values over there. And how to get those values? That is itself is a research question. So this is also not the correct answer. So if I just show you another uh, example, can this 1 second, and discriminant classifiers perform classification on using data points. So over here, just from this coda itself, you can see that it depends on patterns of missingness. It is a it is at random, and imputation is a good choice. So you need to have imputation. Otherwise, if you do not have imputation based methods, you'll not be able to do correct classifications. Okay, so for example, over here also, this is another research paper. The presence of missing values in a data set can affect the performance of a classifier. Obviously, that I have shown already. Let's say you are acquiring ECG, and in some point, the lead is basically uh, uh, it is detached from the surface of the body. So you'll not be able to acquire the ECG signal. So what will happen? It will give you a string of zero. So when you have all string of zero, how will you be able to classify that particular sample? Until and unless you do some sort of missing data prediction. So that is called imputation process. So that means uh, these conditions that they have written over here, technically none of them are the correct answer, but I don't know how they have got that robust to outlier is the correct option. So this is also not the correct answer. And the proof is basically there are n number of research papers that have been written on all these topics, and you can refer to any of them, which basically first deals with the problem and then they try to solve the problem through some new research approach. For example, it could be imputation of data, it could be prediction of missing data, and then you can do the classification, something like that. Okay. 1 second. Okay, so I think I will not be able to show you the implementation today because I don't have the charger with me, laptop charger. So the battery is also 8%. So anyway, it will take very short amount of time to drain. So what I will do, I will share the code snippet and I can show the implementation in the next class as well. And we have solved the week 4 quiz today. So if you have any queries, you can just ask. Otherwise, we can end the session here. Okay, so it seems that there are no question. So
Hello.
yes, 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 please.
For question number 10, I have selected the option D, but it's shown as it's wrong. So
So
shall
that
I get
is
the mark for that question?
so. I will write these anomalies to NPTEL by tonight, and
Okay.
surely as because these options that they have given they are incorrect, so you will get
Oh,
the correct marks. So all of you
okay.
who have chosen the correct answer, or if you have chosen uh, uh, any sort of answers that you thought at that time that is correct, as because the questions, the answers that they have given that is incorrect. So everyone will get marks for that. If you have chosen any of the answer and you have chosen the correct one, so obviously you should get marks. I will write them this particular mail that they have written some anomalies in three of the questions. So they will rectify it and they will update it. It might take some time, but you will get marks. That is for sure. Okay.
Okay, sir. Okay, thank you.
So I think now we can end the session. Just stop recording.